Hello, AP Physics 1 students. We're going to go through one particular problem we didn't have a whole lot of time to do in class, so please have your problem packet in front of you. We're going to look at problem 13. So I want to remind you of the demonstration we've done in class in the back of the room where we had a student sitting on the rotating platform with the heavy weights in their arms outstretched, and we have the person spin in a circle. They brought their arms inwards towards the center. As a result, of course, we saw the person's angular speed increase. This happened because when they brought their masses in, they decreased the value of r for those masses, which meant the value of moment of inertia decreased. As a result, the angular speed increased, and the product, I times omega, stayed the same. That product, of course, is angular momentum. This is a great demonstration of conservation of angular momentum. And I'm sure you've seen this example in other other ways in your life, maybe in sports, for example, in gymnastics. Sometimes when you see someone launch themselves off the vault and they have to do somersaults in the air or coming off the parallel bars, they bring everything in. They bring their arms and legs in. As reason for doing that is they decrease moment of inertia and they increase their angular speed. Or perhaps divers in the Olympics, when they dive from the high platform and they want to somersault in the air, they bring their arms and legs in, they tighten up, and as a result, they decrease moment of inertia and they increase angular speed so they can spin a bunch of times in the air, and they stretch themselves out to slow themselves down from rotating as they enter the water. And of course, the classic example is figure skaters. When you watch the figure skaters go up for their double or triple or quadruple loop, sauerkraut, whatever, they spin in the air. You see that as they go into the air, they bring their arms and legs in so they can spin 2, 3, 4 times in the air. They decrease moment of inertia, they increase angular speed. Or sometimes at the end of their routine, they want to go into fast spin, and so they start themselves spinning, and then again they bring their moment of inertia down, they increase their angular speed. It's very, very exciting. At the very end, to slow themselves down, they outstretch their arms, they make sure they slow themselves down by increasing the moment of inertia. So that's what's happening here in problem 13. We have the initial moment of inertia of the figure skater with her arms outstretched, then she brings them in, they're moving at a certain angular speed, then she brings them in, she decreases moment of inertia. Let's find her new angular speed. Since she's on the ice, there's going to be no net external torque, and that's our clue that we're going to be doing conservation of angular momentum. So in class, we had this equation. Don't write this down just yet, but we had this equation for conservation of angular momentum. L1 plus L2 plus dot dot dot, for however many objects are involved, equals L1 prime plus L2 prime plus dot dot dot. This looks just like conservation of linear momentum when there are multiple objects interacting with each other. But that's the problem. In problem 13, there's only one object. And so we actually change the equation to just L equals L prime. This is a big difference. In linear momentum, we needed multiple objects to interact with each other at some point. But in angular momentum, this can happen with just a single object. The moment of inertia and angular speed change in such a way so that the angular momentum can stay the same. That's what's happening here. So then the question becomes, what equation should we use for angular momentum? So pause the video for a second and write down what equation you think would be appropriate. Well, hopefully you chose I omega because, of course, moment of inertia is given and so is rotational speed. But let's just consider why RP sine theta would not be a good choice. Hopefully in your notes you wrote down that RP sine theta is only for a point mass. So in this case, the figure skater is not a point mass. She's an extended object. This may be a little bit confusing because in a previous problem, problem 14, we had the child jumping on the carousel and we did treat the child as a point mass. So why did that happen? Well, you might recall it's because that the child was very small compared to the overall geometry of the problem, compared to the big carousel. And so that made it most efficient to call the person a point mass. For this situation, the person is the whole object, and so we want to consider the person to be an extended object, and so we're going to write I omega. So how do we write that? Well, on the left-hand side it's I omega, on the right-hand side it's just I prime omega prime. Okay, so pause the video, put your numbers in, verify that you can get the 16 radians per second as the answer. Hopefully your answer makes sense. I mean, you look at the moment of inertia, it decreased by a factor of 4, and so the rotational speed increased by a factor of 4. Everything makes sense. Let's go on to part B. I want to find her change in kinetic energy. So what sort of kinetic energy does she have? Well, hopefully you're thinking about rotational kinetic energy. What's the equation for rotational kinetic energy? Let's write it down. Okay, so hopefully you wrote down KER equals 1/2 I omega squared. Now at this point, let's just remind ourselves that this equation, 1/2 I omega squared, looks an awful lot like the equation I omega for angular momentum, but they're just not the same. So whenever you're writing one or the other, just take that extra second and make sure you have the right version of the equation for the right thing you're finding. So her initial rotational kinetic energy is 1/2 I omega squared. You can go ahead and calculate that with the initial conditions. In a similar fashion, we can find her rotational kinetic energy afterwards, called KER prime. That'll be 1/2 I prime times omega prime squared. Again, you can go ahead and calculate that. But of course, we're looking for her change in kinetic energy. We know change is always final minus initial. In this case, it would be KER prime minus KER. And so you can either calculate the individual kinetic energies separately and then take the difference, or do it all in one shot, which is why I gave a couple different answers here. You'll get one by one method, the other the other. As long as you're getting something like that, maybe some rounding issues along the way, you're doing just fine. The last part here is letter C, and for this I do want to have a discussion about it in class. And so before next class, I want you to think this through and write down your answers so we can discuss it. Okay, so just make sure you have this entire problem done so we can jump right into the discussion of part C next class.